I am Mingyu Lu. Today I will present sensitivity analysis on deep reinforcement learning for sepsis treatment. Reinforcement learning is a machine learning method where an agent would perform an action to interact with the environment, such as Atari, and it will receive certain kinds of reward and enter the next state. By iterating this loop, the agent would learn how to maximize the reward that it received to learn the optimal policy. Since 2017, has been a lot of interesting research in reinforcement learning application in healthcare. With the help of electronic health record, we are able to obtain patient's observation at specific time. And we also know the action performed by the doctor, which is basically the treatment, such as antibiotics or vasopressor that the doctor gives to the patient. Then we could define an artificial reward for this reinforcement learning settings. By iterating this loop, the agent will learn how to treat the patient. But reinforcement learning application in healthcare also face a lot of challenges like the other real-world applications. It's hard to translate high-dimensional continuous state and action into reinforcement learning settings. Designing a reward function is even more difficult because we might not know the incentive or motivation of that certain actions. Even giving a good reward, we might still be trapped in a local optima. Moreover, regardless of the issue that I mentioned, there has been a lot of research show that the final result of reinforcement learning might not be stable and hard to reproduce. And this is a very crucial property in terms of application in healthcare. In early 2019, US FDA proposed a regulatory framework for modification of AI and machine learning. It especially points out that the stable and robust algorithm is the software that we envision. And we consider the robustness of those reinforcement learning applications as the first step to solve those problems. And that's also the motivation for this sensitivity analysis for sepsis treatment. Thanks to the previous work of deep reinforcement learning application in sepsis treatment, we are able to build our pipeline based on their research. So sepsis is the body's extreme response to infection. It will cause multi-organ failure, and it is a life-threatening medical emergency. Early recognition and optimal treatment is very crucial for sepsis treatment. If we could identify sepsis and treat a patient at early stage, their mortality would decrease significantly. Maintaining blood pressure is a major goal for sepsis management. Physicians will usually prescribe intravenous fluid and vasopressor to maintain the blood pressure. So we could frame this sepsis management into a reinforcement learning problem. For this sensitivity analysis, we choose dueling double DQ network as our learning agent. We define a state as patient observation, which is 1 hour laboratory values, including vital sign and other result from a blood draw. Then we compress the patient history with the recurrent embedding model. We also define the reward, which is the decrease in mortality. And for action, as I mentioned, intravenous fluid and vasopressor are two crucial treatments for maintaining blood pressure. So we simplify these two treatments and discretize them into 5 bands according to the dosage, creating a 5 times 5 action space. Here is an example of heat map performed by the physicians. So we especially designed two evaluation metrics for this sensitivity analysis. The first one is the action distribution, which is frequency of each type of action across patient times. The second one is initiating rate, which is the probability of taking a non-zero value given that there was no treatment was given at the previous observation. With these two evaluation metrics, we are able to observe the learning agent's behavior in the outcome policy. Now we can start our sensitivity analysis. First, we're interested in the effect of different time window. Because theoretically, with infinite data, shorter time window is better. It will improve confounding adjustment and allow more flexible and dynamic learning strategies. But with finite data, this ability might be detrimented. So that's why we're interested in investigating the effect of different time window. Here we examine the effect of 1 hourly recorded data and 4 hourly recorded data. The figure on the right, the upper row is the DQN agent trained with 1 hour data. The lower one is the one trained with 4 hourly data. As you can see from the heat map, the 4 hourly data is much more diverse compared to 1 hour data. Our results shows that there's a high variance across different time windows. The DQN agent trained with the 4 hourly data is much more aggressive compared to 1 hourly data. It is more willing to start a treatment and it's prescribed higher dosage for patients across time. We're also interested in investigating the effect of different state representation. For a state in the reinforcement learning, it must satisfy the following rules. It should contain sufficient information to adjust confoundings. It should also contain an effect modifier, which has the conditional average effect of an action on future reward. And most importantly, it should satisfy the Markov assumption, which is the foundation of reinforcement learning. In reality, to maintain the long-term dependency of the history, people will usually use recurrent network to summarize the history. But they choose the embedding model only based on the mean square error or accuracy. And we don't know how would those embedding model have an effect on the outcome policies. So here we analyze two commonly seen embedding model. One is GRU, the other one is LSTM, which is our baseline. We observe that the action distribution of GRU is much more diverse and extreme compared to the LSTM. We also demonstrate lower initiating rate in GRU. In some actions, GRU prescribed 27 times more actions compared to the LSTM. We also analyzed their policies on patients with high risk. We observed that DQN trained with GRU is much more aggressive compared to the agent trained with the GRU. That being said, the treatment being given to this patient is totally depending on what kinds of embedding model that you choose, given that the action and the reward is the same. And we have to be really cautious about this. And lastly, we test the effect of different random seed. As we know, different random seed will cause environmental stochasticity or the stochasticity chain in the learning, such as initialization of weight of hidden layers. So we conduct 5 trials with 5 different random seed and observe the outcome policies. Our results shows that even though the types of action distribution is similar across different trials, there are still huge variance amongst certain types of actions. So even though redundancy is a trivial thing, well, it would have a huge impact on outcome policy, as we demonstrate here. The conclusion is that the choices that we made matters a lot. It will have a huge impact on outcome policy, even though these factors seem similar or even trivial. So we need a benchmark to evaluate the robustness of those policy when it comes to applications. And we consider robustness of these RL algorithms as a stepping stone to the future success. And this is my presentation. Thanks for your attention.